Welcome to Calculus 1, live on the internet or being viewed in the future somewhere. Hello, future math students. So we are in chapter 4 now, the home stretch. If it's colored, it means I've got it ready for you guys to use. If it's not colored, it means it's like I'm getting there. So I'm just a few days ahead of you right now, but I'll catch up. We're going to be probably a day and a half, 2 days on related rates. We're going to do that today. Linear approximations, which we talked about before, and we're going to use in a slightly different way, the idea of differentials, and then a whole bunch of different applications of derivatives. So we're going to take all the derivative stuff we learned, and we're just going to apply it to a whole bunch of different circumstances. Some are purely mathematical, some are very applied.
So is this just the story problem chapter?
This is the story problem chapter. Please, more enthusiasm there. Oh, that's the whole point of math, is like solving problems. So there is a book. I don't know if you guys open it at all, but it's a wonderful book. It's got pretty pictures. We'll take a look at the balloon problem today, and there's a bunch of other cute ones today, like launching rockets. That's another cute one. So we're going to do cute problems today. All right, look at the book sometime. My guess is your usual strategy is click on the homework, try, watch a video, ask in class, which is okay. That's not bad. There's an excellent first video I posted here. I highly recommend you check it out. It's from a guy called 3 Blue, 1 Brown, and he just does fantastic stuff. That's not him. That's some advertisement there. But I highly recommend you check out this video. It reviews implicit differentiation, which we talked about before. We're going to do that today. And then he goes on to talk about how it's related to related rates. So without further ado, related rates. Again. Here we go. So there are many instances in our reality where one thing changing forces a bunch of things around it to change, right? Like riding a bicycle. Like somebody at Apple deciding to change the price of the iPhone, right? The price goes up. Do more people buy it, you think? The price goes up? Probably less people buy it, right?
Depends.
Yeah, so it depends, right? Yeah, there are other things involved, but the basic idea with supply and demand is the price goes up, then people buy less, so supply ends up going down. But there's tons of examples of things changing together. So I'm just going to give you one example for now, and then many more to follow. So let's consider a coffee filter. Okay. Make believe it's a perfect cone. What's that? I do?
Yeah.
So let's say in this particular instance here, so the defining characteristics of a cone are its radius at the top and its height. So I need an H and I need an R. Anybody remember the volume of a cone?
Something.
Almost. It's going to be cubic units because it's volume. Yeah.
Is it half volume of the cylinder?
It is not quite half. So in 2 dimensions, triangles are half of a rectangle. In 3 dimensions, pointy things are a third of their non-pointy counterparts. So it's 1/3.
1/3.
Yeah. So a cylinder, if this was a perfect cylinder, it has a circular top, so you get a pi r squared for the top, and then you multiply by the height if it was a cylinder. Since it's a cone, it ends up being 1/3 of that. So that's the volume of a cone. So let's suppose for this particular cone, my pen is not tracking right, and reset it. This must have slipped a little. So for this cone, let's say it's a 10 centimeter diameter and a 10 centimeter height. So diameter equals 10 centimeters, and let's say the height equals 10 centimeters. So if the diameter is 10 centimeters, what's the radius? Radius would be 5 centimeters. So what that tells us is it basically tells us the slope of the side of the cone. Okay. And that's important because how many variables do I have to work with here?
3.
I have 3 variables. So whenever possible, I like to limit the number of variables. And on this particular cone, I can, because the ratio of the, whoa, my pen's freaking out. The ratio of the radius to the height on this particular cone is always 5 to 10. That's the slope of the side of the cone.
And negative h.
That is just supposed to be an H. Sorry, that was an artifact of my pen freaking out. So cleaning that up a little bit, I get that the radius, all kinds of pen drills today. The radius is equal to 1/2 of the height when I clean that up, right? 5/10 is 1/2, multiply the H to the other side. So I can narrow down my volume formula a little bit on this particular cone. And on any cone, you just take the radius of the ratio of the radius to the height, and that'll narrow your variables. So for this particular cone, I get volume is 1/3 times pi. Radius is really the height over 2 squared times h. Cleaning this up a little bit further, what do we get? 1/3, there we go, pi h squared over 4. And then 4 times 3 in the denominator is 12. Bring the pi into that. I get pi 12ths times the height cubed is my volume formula for this cone, just based on the height. So next thing we're going to do is we're just going to imagine that something's changing here. So back to my cone. What I'm going to do next is start pouring hot water into my cone. And let's suppose I'm pouring at a constant rate. And let's say it's, how about 200 cubic centimeters. That might be a little too fast. Let's go with 20 cubic centimeters per second is what I'm pouring it in at. So then the question is, how fast, if I'm pouring at this rate, how fast is the height of the liquid in the container changing? Okay, right? Because as I'm pouring water in, isn't the height going to change? Mm-hmm. Yeah. So the key here is that the change in volume is going to be related to the change in height in the cone. So what, the 20 cubic centimeters per second, what is that giving me? Is that my change in volume? Is it my change in height, or is it something else? It's change in volume. Cubic centimeters is volume. Yeah, so I'm pouring in a volume of water. So that's the change in volume. So what I gave you right there is dV dt. So I'm saying dV dt is positive 20. The volume is changing over time. That's going to force the height of the liquid inside the container to change over time also. Okay. So our formula, there we go, was that V was equal to pi 12ths h cubed for this cone. Right. Reminder, every cone has this formula right there. Once you know the top radius and the height of the cone, then you can get a unique formula just based on the height if you want. So we need to take the derivative of this, but the catch is we're taking the derivative with respect to time, not with respect to h. That's the idea of implicit differentiation. So what we're going to do next is we're going to take the derivative on each side with respect to time. So that, oops, on one side I have the derivative with respect to time of the volume. On the other side I have the derivative with respect to time of all of that stuff. Now, taking the derivative with respect to time isn't much different than taking the derivative with respect to x. It's the same idea. But what do we have to assume about v and h here? They're functions of time. Yeah, they're both functions of time. At any time I look, I'm going to get a slightly different volume. I'm going to get a slightly different height. They're both functions of time. So then what rule is going to be very important here? The chain rule. Right. So this is just implicit differentiation, chain rule, except we're using time as our variable most of the time. All right, so derivative with respect to time of v is
20.
Is 20. That's my dv dt. Okay, so sometimes that's given straight out, sometimes it's not. In this case, it's just 20. Now, on the other side, what do I do with the pi over 12? Just gets carried along, right? It's just a multiple, so it's just hanging out. And then I have to apply the power rule to h cubed, which gives me what? 3h squared, but the chain rule says multiply by h dt. So I'm going to pull out the 20 for just a sec because I want to talk about this general scenario. So I'm just going to call that dv dt. So what this formula tells me is how the rate of change of volume is related to the rate of change of height. And it's related by this funky multiple, which involves knowing the height at some particular time. So we have to know that information too. Okay? All right, so just some given information. So we would have to know a variety of things. We'd have to know a time instance to look at, and then we have to know what h is at that time also. So I'm just going to throw out some numbers. So let's just suppose at, let's go 1 second into the pour. The height is 1.5 centimeters. What is the rate of change of the height? So the procedure on these problems is going to be pretty much the same all the time. You've got to come up with some equation, and then you've got to implicitly differentiate that equation. The fewer variables, the better. So if you can find a way to limit variables, do it. And we did. Again, so we started with v. I'm just going to reiterate some information so you can not copy this part. Pi over 12 times h cubed. That led us to a differential equation, because it's got derivatives in it, dv dt equals, and I'll clean that up a little bit. The 3 is going to clean up with the 12, and then we're going to get an h squared dh dt. And then once you clean it up and you have your derivative, then you just plug in what you know, and hopefully what you don't know is what pops out in the end. So do we know dv dt here?
Yes.
Yeah, so we were given that that is 20. And we'll double check the units in a moment, make sure that's right. Pi over 4 is just a constant. Do we know h? 1.5. And we don't know dh dt, but that's what we're looking for, isn't it? So can't we solve for dh dt now? Totally, yeah. We're just going to take our 20, divide by this stuff over here, and out pops our rate of change of the height at that instant. So let's whip out some calculators, and then we'll double check the units. Make sure we agree on the answer. So, stay here, pen. So I have 20 divided by parentheses pi over 4 times 1.5 squared, all in the denominator. I get about 11.3-ish. Carter says yes. Anyone else? So again, we're taking our 20, dividing by the pi over 4. And we don't need to be super meticulous about solving this one part at a time. We just need a number, right? An approximate number here. So for me, h dt is 20 divided by pi over 12, pi over 4, clean it up, times 1.5 squared, and I found it's about 11.3. Okay, what should the units of the 1.3 be? Let's double check that.
Cube.
What are we measuring here? We're measuring change in height over change in time.
Cubic centimeters.
Just
Centimeters over
centimeters.
No, centimeters. Yeah, height is just measured. So this should be centimeters per second is what it should be. All right, so now we're going to make sure that that happened. What was the units of the 20?
Centimeters cubed per second.
Okay, that was centimeters cubed per second. Okay. And then down here, pi over 4 is unitless, but the 1.5 did have units. What were the units of the 1.5? It was a height, it was centimeters. So in the bottom, I have centimeters squared. So cleaning the units up here, I get centimeters cubed over s times 1 over centimeters squared, which leads to centimeters per second. Okay, so the units worked out right. And that's something you should check with these. When will things go wrong? If you either mess up your equation or the derivative, then the units won't work out. So if the units won't work out, either you had trouble setting the units or you have an error somewhere in your derivative probability. Okay. All right, related rates. Let's try another one. And there's a harder version of this problem in the homework that we might get to today. That was a cute one. What's that?
Can we do a homework problem?
Can we do a homework problem? Oh, sure. We're going to do homework number 3. Because 3 is a magic number. All right, so let me blow this sucker up a little bit. Yeah, we got a ship sailing. Hey, it could be worse. It could be 2 trains heading toward each other or something like
Is it
that.
important that it's at noon?
Yes. All right, so at noon, ship A is sailing 30 nautical miles due west of ship B. Ship A is sailing west at 22 knots. Ship B is sailing north at 20 knots. How fast in knots is the distance between the ships changing at 5 p.m.? Oh my. 1 knot is 1 nautical mile per hour. So, first thing, attempt to draw a picture of this.
There's a boat, and it's heading this area, an arrow. Like,
So
this
there's
way with an arrow.
Yeah, so mess around, just draw a picture.
there's 2 ships.
There's 2 ships. They are not heading in the same direction.
Let's do this.
So I'm gonna let you struggle with the picture for a second. In almost all of these problems, you're gonna have some kind of picture to go with.
What's the shorthand for nuts?
Knots, I don't know what the shorthand for knots is. I just call them knots. They're telling us the knot relation to nautical miles per hour because we're going to need to check units on this, make sure we're doing things right. All right, so I'm going to copy that in my clipboard and attempt to draw a picture.
Wait, is it still up?
I'm going to bring it back, make a snapshot of it. All right. Okay, so ship A is west of B. So let's see. That would be the left coast. So that's the left. So I got ship, and then what is ship B doing? Ship B is going north. Okay. So B maybe starts off here. It's going to head north. A is somewhere over here. It's to the west. It starts out 30 nautical miles away.
And keeps going.
And keeps going at a rate of 22. So from 30, I'm going to add on 22 knots per hour. So T is hours here. What's that?
I thought they were just gonna hit each other.
No, they're sailing away from each other. Because A starts west and keeps going west. Right? B starts off right where I have it, but heads north at a rate of 20 knots, which is 20 nautical miles per hour. So that its formula for its distance would just be 20t, where t is hours here. So one thing I need for this is distance equals rate times time. This one has an extra starting position, so it's like a straight line kind of thing. And then what am I actually trying to calculate here? How fast the distance between the ships is changing. So at some point in time up here and there, there's going to be a distance between them. And what shape do we have there?
It's
right.
A right triangle, yeah. So I'm going to call this distance C, for lack of imagination. And I know that C squared equals A squared plus B squared. That's way too many variables. I got a T, I got an A, I got a B. So we need to narrow this down a little bit. Well, don't we know B's distance? It's 20t, right? And we know A's distance, it's 30 plus 22t, so I'm just going to drop those in. So A is really 30 plus 22t. It's got to be squared to get C's distance. B is really 20t. It's got to be squared according to the Pythagorean theorem. So now I've got it down to two variables, C and T. I like that better. Anywhere possible, we can get it down to two variables, we're way better off.
Do we need to start foiling things?
What's that?
Do we need to start foiling things?
We should multiply this stuff out. Yeah, we should clean it up as much as possible before we take the derivative. So that means we're going to have to take 30 plus 22t times 30 plus 22t.
900.
So that's going to give me what? 900 plus
66 plus 66.
is 132, 10, 1,320.
Yeah.
I got a yes and a no. Is it?
Yeah, it should be.
I
It
said
should.
yes.
No, I said
I
yeah.
said yes.
Okay, oh, you did say yes, all right. So that's, so 30 times 22 is 660. 660 plus 660 is 1,320t. Plus
484 t squared.
484, that's 22 squared, right?
Mhm.
Okay, t squared plus 400 t squared, when we take 20t times 20t. That cleans up a little bit.
Add.
Oh, yeah.
So that gives me 884 t squared. Okay, so new page, run out of room, let's pick a new color. So c squared is 884, oops, that's not a 4. I can't get ahead of my brain. T squared plus 1,320t plus 900. All right, so we have a relationship that gives us the distance they are, the square of the distance they are apart at some time t. Now you might think, hey, let's take the square root of both sides, but taking the square root, derivative of square root is kind of a pain. I'd rather take the derivative of square than square root. You with me?
Are we just gonna ignore the 20t squared? Or are we
No.
going back to that?
We've got it.
Oh, we did?
Yeah, so that's the 400t squared. 20 times 20 is 400.
Yeah.
We left it at 5, so we should just.
We can't plug in the 5 yet. We have to first take the derivative and then we can start plugging stuff in. Yeah. So the procedure is get all your relationships set up and then clean up the equation as much as possible. That's step 1. Step 2, take the derivative. Step 3, plug stuff in and hope for the best. So now I'm ready to take the derivative, and I'm taking the derivative with respect to time. So d dt of c squared equals d dt of all that stuff So let's see. Derivative of c squared is 2c
Times
Times
DC
DC.
dt.
times dc dt.
What's the differentiation?
On the other side, we have to double 884, which is something like 1,768. Thank you. T plus 1,320, and then the 900, its derivative is 0, so it's gone. And ultimately, I'm trying to find the rate of change of the distance between them, which means this is what I'm searching for right there. So I'm hoping that I have a time and I have a c at that time. So now we're going to start plugging stuff in. So go back for a second, see what information we have. Let's see, we're interested in 5 hours later. So that's good. New color. I know that t equals 5. I'm going to plug that in a minute. Right? I'm going to need that here. What else do I need to know?
C.
I need to know c at that instant. So back here, I have to calculate what c is at that instant. So a couple ways I can do it. I could plug in here. I could plug in there. I could plug in up there. We got to figure that out to continue here. So I think I'm just going to go back here and do it. So let's see. If I plug in 5 there, that's going to give me 5 times 20 is about 100. So I'm going to have a 100 squared from the Pythagorean theorem. If I plug in 5 here, I get 110 plus 30, which is 140. I'm going to have 140 squared. And then to get c by itself, I'll have to take the square root of that. So at 5 hours in, whatever that is will be the value of c, and there's the value for 5. So now we just plug that stuff in and see what happens. And I don't care about simplifying this too much. I just want to come up with an answer here. So then, oops, that's a little pen. Nope, pen. There we go. So for dc dt, I'm going to plug in 5 there. So I'm going to have a 1768 times 5 plus 1,320 divided by 2 times that square root. 140 squared plus 100 squared. And then my fingers hit my calculator and we'll double check units after we get a number. All right, I think I got most of that in my head. Might as well use Desmos since I have it out. So fraction 1768 times 5 plus 1320 over 2 times the SQRT of 140 squared plus 100 squared. And Desmos tells me it's about 29.5-ish. I did it right. 29.5269 if I want more decimal places. Now, one cool thing about some of these problems is they say you can just enter a mathematical expression. So at this point, I could either type my decimal equivalent or I could type the mathematical expression. All right, so I'm going to try it both ways, see how the computer reacts. Oops, where'd Desmos go? So usually if I'm plugging in a decimal, if it doesn't say, I usually do about 5 decimal places. So 29.5269-ish. 25.5269. All right, so before I hit enter, I just want to double check some units here. Where's my notes? All right, so let's see. Units. Oh, this is a hard one to check units on. What's that?
Do we have checked units every time?
It's usually a good idea. So let's go back here to double check. So what do we got here? 20 is nautical miles per hour times hours gives us nautical miles. So I don't know a good abbreviation for that. So I'm going to call them N's. So that's in nautical miles there. Same thing's going to be true here. 30 is nautical miles. That product is nautical miles. So then I took nautical miles and squared them, but then I took their square root. So what's C in?
Yeah.
Nautical miles. It's in nautical miles. All right, so that's all looking good. Back here, what do we got? C squared is measured in nautical miles squared. So this derivative over here is nautical miles squared per second because I differentiated with respect to time. But then I'm dividing by C. What's C measured in?
It's not per hours, it's our time.
Oh, hours, not
Hour.
seconds. Yeah, thank you. Hours. Other problem, second. Hours. C is measured in nautical miles, right?
Yeah.
So if I divide the nautical miles out here, what do we end up with? Nautical miles per hour, which is knots, which is what dc dt should be. So yeah, I think we're okay on the units there. So hopefully I calculated stuff right. Submit. Oh, I got something wrong. What did I get wrong? 29. Oh, I can't read what Desmos tell me. It's 29. Helps if I could transcribe, and I got it right. And alternately, you could just type in that expression too. So you could have typed in parentheses 1768 times 5 plus 1320. You just got to use parentheses carefully. Divided by 2 times the SQRT of 140 squared plus 100 squared. Close the root, close the denominator. It says if I don't close the parentheses, it should give me a syntax error, unmatched parentheses. So make sure it doesn't give you an error. How does the answer? It just gives me the decimal, submit, and it says, yeah, that works too. Pretty cool, huh? All right, let's try another one. How about, ooh, I like number 5. No, number 7 is difficult.
Let's do number 7.
We'll do number 7 next. We have time, I think. All right, so I just want to give a couple of pieces of information about some economics in this problem, and then we'll set forth on the problem. A 1, oh fine. I was hoping to be a little harder than that. All right, so I talked a little about marginal revenue a while back. We'll get to that again in a couple of days. But just the idea of revenue. One super simple version of revenue is just price times quantity. Okay. You got some stuff you're selling. T-shirts. You sell them for $10 each. You sold 100. What's your revenue? It's 100 times 10. Okay, so price times quantity. So let's go with that. Other thing about price and quantity, if you would consider those two. So usually if the price is really high, quantity, people aren't going to buy as much. But if you make the price a little lower, people are going to buy more, right? So here, didn't sell much at a high price. I sold a lot at a low price if I'm doing price versus quantity. So often, a simple example of a price versus quantity equation is just a straight line downward slope, something like that right there. Okay. So for example, perhaps price is equal to 1,400 minus X. So in this case, the graph, that would be $1,400 up there. So if I price it at $1,400, nobody's going to buy any. And if I give it away for free, I'll be able to get rid of 1,400 of them. Okay. If I take that into consideration, then revenue is just whatever the price is. Well, price is dictated by that quantity equation right there. So 1,400 minus X times quantity, which is what X is. In which case, I get a revenue equation that looks something like 1,400X minus X squared. Okay, so that's a super simple economics view of supply and demand and what revenue would look like based on that. You get this quadratic equation out of it. Somewhere in the middle is the optimum price, which gives you the highest revenue, right? Because this is an upside down parabola, you all agree?
Yes.
So there is a maximum revenue that can come out of that. We'll talk about maximum revenue later. Now let's go look at the problem we were, so that's just a little background for this problem. Does that equation look familiar?
Yeah.
It's right there.
You needed calculus to do economics.
You do, it turns out. Revenue has a ton of, economics has a ton of math in it. And once you get past first year economics, it's like all math.
Lovely.
Yeah.
Sounds fun.
It is fun. I was forced to take an economics course as an undergraduate. Actually, I wasn't forced. I had to take something outside of math and science. So I chose economics. So I took a 300 level economics course and it was just calculus. That's all it was.
You had a grand time.
So I was just kicking butt in that course and all the economics students were dying, right? Because they didn't have as much math as me. So anyway, so we're going to do this problem right here. And it's just, again, that revenue equation is just based on a simple supply and demand model that I just went over a second ago. So nice thing about this equation, it only has two variables. Pretty cool. Okay. Here, though, they give us that the sales, oops, can't draw on that. The sales are changing, increasing at a rate of 35 units per day. Okay. Sales, that's my quantity of stuff, that's my X. So what would I call that 35 using calculus ideas? That's the derivative of the sales with respect to time. Yeah, so that would be dx dt is what they just gave me there. All right, so I'm gonna plug this into my worksheet and we'll nail this sucker. Screenshot so we have the appropriate information. Do it. So I've got the revenue equation. I'll rewrite that in a second. I'm going to copy down some other important information. The sales are increasing at a rate of 35 units per day. That is dx dt. And it is a positive 35. Okay, so we have to pay attention to increasing rates, decreasing rates, positive and negative values. This one's positive. And we want to know how rapidly the revenue is increasing when they've sold 400 units. So they're saying at some instance, X is equal to 450 units. And I'm going to need that in a moment. So now we take our given equation. Oops, I'm not heard E yet. Ahead of myself. Revenue equals 1400X minus X squared. We need to implicitly differentiate with respect to time. So we are going to dt this stuff. So derivative of r with respect to time is the derivative of r with respect to time.
1400.
dr dt. That's going to be equal to 1400
Minus 2.
oh, dx dt. Yeah, x is a function of time. So although the derivative of 1400x is 1400, chain rule says you have to multiply by dx dt. Yeah, that's the thing you always got to be thinking of in related rates. Every variable present is a function of some other variable, in this case time. Minus 2x dx dt again. All right, so we're asked to figure out how rapidly the revenue is increasing. So we're trying to calculate the r dt. That means we need to know dx dt. Got it. And we also need to know x. Got it. So then we just plug in the numbers that were given. So in this case, I'm going to find that the change in revenue is equal to 1400 times 35 minus 2 times 450 times 35. whipping that into a calculator. So 1,400 times 35 plus, let's see, it was 2, minus, yep. Minus 2 times 450, is that right?
Yeah.
Times 35. So 1,750 if I type that right? No, 17,500. Sorry, I missed a zero there. All right, double checking units. Let's see. R is measured in dollars. So this is dollars per day. And the 1,400 was dollars. So we have dollars times units per day. Oh, let's see, is that right? I believe it's right.
That's right.
All right. So, and again, this is probably one of those where it says you can enter a mathematical expression. So you could either type the number that you got, is that right? Number of zeros, yep. Or you could type the expression that you used to get it. Cool. All right. Let's do a hard one. We're probably not going to have time to finish it, but we'll have time to set it up. We're going to spend another day on this. Number 7 is rather challenging, I thought.
Oh, look how many words there are.
So water, yeah, more words. Water is leaking out of an inverted conical tank
What?
What even is that?
at a rate of 11,400 cubic centimeters per minute at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 15 meters and the diameter at the top is 7 meters. The water level is rising at a rate of 18 centimeters per minute when the height is 2.5 meters. Find the rate at which water is being pumped into the tank in cubic centimeters per minute. Ooh, exciting. Okay, so we're going to start by drawing a picture. No, we can set it up though.
Conical shape is a fishbowl.
No, cone. Conical means cone. So it's just a cone.
I started by
Yes, draw a picture of a cone. So, oops,
Then I
screenshot.
suppose we should write down what height and diameter.
Yeah. All right, so let's see. We got a cone. Inverted means it's pointing down.
Weird water tank.
Our height
Yeah.
is 15
Height is
meters.
15, so from here to here is 15
Our diameter is 7.
meters.
It's a big tank.
Diameter is 7, so the radius is
3.5.
3.5. So R is 3.5. So then a couple of things we're going to need. So first thing we need is just the volume 1/3 pi r squared h. Too many variables, right? 3 variables. But we know a relationship for the slope there because we have the height and the radius. So the radius versus the height is always at a ratio of 3.5 to 15. Now, first thing is, are the units consistent? Let's see, the 7 was in meters, the 15 was in meters, so that's good. But I see another problem up here that's going to hit us in the butt later.
That's 18 centimeters per minute.
Yeah, they give some centimeters in different spots. So centimeters per minute for the 18,
Is it 2.5, not 3.5?
7 divided by 2 is 3.5.
3.5.
Yeah, so the radius is half the diameter. So we're going to take 7 over 2 to get the radius. 1,400 cubic centimeters per minute. So at least both are per minute, but we do have a problem with centimeters in one spot and meters in the other. We're going to have to make a decision about that.
And there's when the height of the water is 2.5 meters.
Yeah, we have a 2.5 meters. So I think we're going to have to change change to, let's see, what do they want the final answer in?
Minute.
Cubic centimeters.
Cubic centimeters per minute. So we're gonna have to change all the meters to centimeters is what I would say to make this easier.
Tomorrow.
And we're gonna have to do that tomorrow. Yeah, so you have enough information to try and finish this, so give it your best shot. We'll do it again in class tomorrow, picking up from here. I'll keep grading your tests. Maybe I'll get them done tomorrow. It's a good possibility.
I don't really want to know yet.
I'm gonna wait till next year to find out.
Yeah.
How about you wait? How about you just tell me? How about you just tell me when I die?
We want to take the